Hello everybody and welcome to High Performance Computing. My name is Marcel Aach. I'm working at the Simulation and Data Lab, Fluids and Solids Engineering at the Jülich Supercomputing Center in Germany. And I will be giving today's lecture on the topic of hyperparameter optimization and automated machine learning. What we will cover in today's lecture is to give you an overview over what are hyperparameters, then look at different algorithms to optimize these hyperparameters, split into adaptive scheduling and adaptive selection methods, look at which algorithm to use in which case, and finally also go a bit into how to use hyperparameter optimization efficiently on high-performance computing systems. Now, just to make sure everybody's on the same page, what are hyperparameters? So the hyperparameters are the parameters that influence the learning behavior of your machine learning model and are usually set by you as the user or the developer before the training. This can include architectural parameters such as the type of machine learning model you are using, the number and kind of layers in your network, or the activation functions. But more prominently, it refers to the parameters of the optimization process, such as the type of optimizer, the learning rate, or the momentum value. But that's not all. Sometimes also the parameters of the whole machine learning pipeline can be included. So if you're working with images, you could also include the image pre-processing steps, such as normalization or rotation, into your HPO pipeline. To put this all into perspective, there are three areas where you can tune predefined parameters. One is the so-called neural architecture search that just deals with architectural parameters. Then we have the so-called classic hyperparameter optimization. And then if you add parameters of the pipeline on top, you get what is commonly referred to as automated machine learning. You would not be here if you did not already know just how important hyperparameters are for the success of your machine learning model. And just to visualize it again, here's an overview of the learning curves of a simple ResNet model, which was trained on the Cypher10 dataset. And from this plot, you can see the importance the learning rate makes on the difference between getting a good model, which achieves more than 80% classification accuracy, or getting a model that learns nothing at all. So if you get 10% accuracy on Cypher10 and there are 10 classes, that means your model is just randomly guessing. And this also actually gives you a first hint towards why the problem of selecting the hyperparameters is so hard. When we look at these curves here, we see that there's no general prediction possible. So you usually cannot say a large learning rate is good and a small learning rate is bad. But these decisions are usually very, very fine-grained. A bit of terminology. So when I talk about search space, I mean the hyperparameters and the intervals that these hyperparameters are sampled from. When I talk about a configuration, I mean a set of hyperparameters that is sampled from the search space. And when I talk about a trial, I mean one training run of such a combination, such a configuration of hyperparameters. And I want to mention this here already because it's very important. When you do hyperparameter optimization, you need three data sets. So first, you need a training data set that you train your machine learning models on. Then you need a validation data set that you validate the performance of your different hyperparameter configurations on, and then select the best hyperparameters based on the validation set performance. And then in the end, you also need a completely untouched test data set that you then again test the performance of your hyperparameters on. Now, the main reason why hyperparameter optimization is hard is that the search space is often a mix of lots of different types of parameters. So the number of layers is, of course, a discrete value. while the learning rate is usually a continuous value. And in these settings, you cannot compute gradients like we do with gradient descent to find a minimum. So instead, we need to look at other methods to find a minimum here. And this is also the main reason why HPO can be very computationally expensive. You can only evaluate the performance of a configuration of hyperparameters with total certainty after you have the model completely trained. So after you have run the training for all the epochs, which of course becomes computationally very expensive. And actually in today's setting, because there is usually a general lack of guidance on how to approach hyperparameter optimization, today this is still mainly done via trial and error by the human developer. So in order to find better approaches, we're now going to look at HPO algorithms to do this hyperparameter optimization in a more systematic way. And the easy or naive way when you approach this problem is to either do random search or grid search. In random search, as the name suggests, you just sample randomly from your hyperparameter search space, while in grid search, you evaluate every possible hyperparameter combination there is. Now, the interesting thing is that especially random search is already a very good starting point. So when you don't know anything about your problem, you should at least do random search. And from a parallel computing point of view, both methods, of course, are embarrassingly parallel, as there's virtually no combination required between your different hyperparameter trials, and they can run independently of each other. But at the same time, you're also wasting lots and lots of computing resources on hyperparameter trials that probably have very bad performance and which you shouldn't really continue fully training. So how can we accelerate this and make it more efficient? There are two ways to approach this. We can either do an adaptive selection of the configurations that we want to evaluate. So this means using Bayesian optimization or evolutionary optimization to pick better configurations. The main problem here is, which I've already mentioned earlier, usually our search space is very high dimensional, and this can make it hard for some of these methods to work in these very high dimensional search spaces. The other option, which we will focus on mostly here today, is to perform adaptive scheduling of your trials. And this means that you stop trials with bad performance and instead use the computing resources for trials with better performance. And the main problem we have here, of course, is how do I decide which trial is a bad trial and which trial is a good trial when I don't have much information about the problem available. And we can already see here that we can get some information by looking at these learning curves at the same time and then comparing them to each other. So what we see here again are learning curves for ResNet models trained on Cypher10 and TinyImageNet to computer vision benchmarking datasets. And we can see that because we have so many learning curves available that we can start comparing one learning curve to another, and then we have a guess of which one of these two is the better learning curve. And this is then where something called successive halving comes into play. The basic idea here is very simple and again based on the concept of early stopping bad trials and allocating their resources to more promising ones. And we can do that at multiple points in time. So in practice, it would look something like this. We start out with an initial number of configurations, then train them for some time. Then after a few epochs, for example, we do a relative ranking of all of our trials, for example, by the validation loss or validation accuracy. We terminate then the worst 50% of trials and continue training only with the better half. Then we train for some more epochs and repeat this process again. What then happens is that in the end, we will hopefully end up with just one single trial that has the lowest loss. So in this figure, that would be the dark green line here. Well, this looks good. The main question here is then, how do we balance our computational resources? Should we run more trials in the beginning to get more exploration, or should we run our trials for longer in order to get more exploitation? This is where the hyperband algorithm extends the classical successive halving approach by performing successive halving with different levels of aggression, so to say. So what happens here is that in the first, you have these different rungs. And in the first run, you make a cut every 20 epoch. In the next run, you make the cut only every 40 epoch, and so on. And the hope is then that this actually catches the trials that start out weak but get strong later on. So in this example, what we would do is to have a total number of trials and then actually train a few of these trials without any early stopping. Then train a certain other number of configurations with one early stopping step, a larger amount of trials with two early stopping steps, and then have a really large number of configurations which we then very aggressively early stop. And Hyperband does all of this at the same time. Now, especially when you're moving to a setting where you have lots of parallel computing resources available, such as is usually the case on an HPC system, you can run into performance issues with this classical hyperband approach. And the problem here is because these decision points where you want to measure how good a trial is compared to another trial, these decision points are at the same time also time barriers. So in order to make the decision here, which of these trials is the better one, you of course need to have both, at least two results available to make the decision which of these trials is the better one. But if your trials have different runtimes, which in a lot of cases happens when you have, for example, a different number of neurons in your neural network, the neural network with fewer neurons usually runs much faster than a neural network with a lot of neurons. So in this case, then you have the problem that your algorithm is very sensitive to these stragglers, and these faster trials need to wait for the slower ones before they are allowed to continue. And when you have a very parallel setting with lots of different trials running in parallel, this can essentially degrade your performance by a large factor. We therefore need to move to an asynchronous setting, and here comes the Azure algorithms into play. What this algorithm does is that at each of these decision points, it looks immediately at the performance of the incoming trials and then continues training them based on the information it already has available. So looking at this visualization, on the left we see the hyperband algorithm, which at each of these decision points needs to wait until all of the trials have reached the decision point before continuing the training, compared to the Azure algorithm, which at each of these decision points just continues training some of the trials, even if they in the end up not being the good choices, not being among the trials that achieve the lowest loss. It still continues training them because it doesn't want to run into these straggling problems. So what you're doing here is that you're continuing training some trials, and if they are end up being among your worst trials, you just terminate them later. It's not a bad thing to do, but if they end up with good performance, you are lucky that you continue training them, because then you get your results in the end much faster. And this is the main reason why Asha is very efficient from a computational point of view. Also, a brief overview of the adaptive selection method of hyperparameters. The idea here is to build a surrogate model that is cheap to compute, but can mimic the performance of your original machine learning model. And there are many different algorithms and libraries available. For example, many ones use Bayesian approaches such as SMAC, Dragonfly, or Tuna, or DeepHyper. The main challenge they all have to deal with is how to handle lots of parallel results coming in at the same time, as Bayesian optimization is usually a sequential process. And as already mentioned, sometimes also Bayesian optimization has problems in very high dimensional search spaces. And it's also possible to combine this Bayesian optimization with the hyperband approach that I've shown you earlier. A special case I would like to address are these non-stationary or dynamic hyperparameters, so the ones that change during the training of a model. The prime example here, of course, are changing learning rates over the number of epochs. And while here lots of predefined schedulers are already available, such as the cosine or exponential annealing schedule, you can also optimize for learning rate schedules on your own. And this is where population-based training, originally introduced by Google DeepMind, can help. Here we start out with an initial population of trials, which is then again trained for a certain amount of time. Then again, we measure the relative performance of the trials, start comparing them to each other, and the worst half of the trials is terminated. What makes this approach now special is that the trials with bad performance copy the state of the well-performing models, including all the architecture weights, and then apply small mutations to their hyperparameters, such as changing the learning rate by a small factor. And then they continue training with these models. This approach is generally referred to as evolutionary optimization. And there are, again, lots of other libraries that do similar things. For example, Nevergrad or Propulate, which is also a hyperparameter optimization tool that is optimized for usage on HPC systems. Now that we have seen some approaches to HPO, the question is when to use which algorithm. And here I have an overview which was adapted from a colleague, but it's also sprinkled with some of my own experience from doing HPO on the large scale for quite some time now. So what we need to look here is first the dimension of your search space. If your search space is very low dimension, so if say you have just two hyperparameters that you want to optimize for, then it's probably the best idea to do random search and just sample configurations from the search space and train them until completion, or do the same thing with grid search, sample every value and look at how your models perform. Again, this is a pretty simple starting point, and if you don't want to deal with advanced hyperparameter optimization, I would always recommend to at least do a random search. And usually when you just have two hyperparameters to optimize for, you can also afford to do this from a computational resource perspective. But if your search space does get larger and you have, let's say, more than 3 hyperparameters, for example, then as a next step, you would look at how long each of your trials run. And again, here, if your runtime per trial is really short, let's say less than 5 minutes, and you have HPC resources available, then you probably still can afford to do random search. However, deep neural networks, as you know, sometimes, or actually in the majority of cases, probably do not train for just a few minutes, but usually training them takes on the scale of several hours. So then we move on to the next decision point, which is to look at if your models you're training, the type of models you're training, would be considered late learners. And late learner means that the largest improvement of your training run happens during the second half of training. Because if that's the case, you, of course, it could happen to you that you start terminating very good trials way too early. I have to say, from experience, and again looking at these classical learning curves here, we usually see that the biggest improvement in performance happens during the first, let's say, 25% of training. So it's usually safe to say that machine learning models here are not late learners, and then you can very safely use methods such as Hyperband and Usher. However, if you have this special case where your model could be considered a late learner, then we move on to the next decision point, which is to look at the total number of trials you can afford to run with your compute resources. And if that's smaller than 200, it makes sense to use things such as Bayesian optimization or Bayesian optimization combined with Hyperband. However, if you have a large compute budget and can afford to run trials in the thousands, then you are again back to the methods from the beginning, which is random search, or of course the more efficient version of this, the Azure algorithm, because with such a large number of trials, usually not so many things can go wrong. And apart from this, of course, also we have the special case where you have these non-stationary, these dynamic hyperparameters such as learning rate schedules. In those cases, you should switch to evolutionary approaches such as the population-based training. There are, of course, also some totally different approaches to the problem. So we could also use reinforcement learning, and here I have a reinforcement learning agent, select the parameter combinations, and then use the performance of these combinations as a reward. When you use a special representation of your architecture search space, it can actually become possible to compute gradients. This is called differentiable architecture search. And then, of course, you can also do gradient descent on the architecture search space to find a minimum. Some very interesting work is looking at so-called zero-cost proxies and how they relate to the final performance of a model. One example of such a zero-cost proxy is to just take the total number of parameters of the neural network and make a prediction with that, like a regression, and this works surprisingly well. And in the time of very large foundation models, where you can probably only, even with HPC resources, afford one training run, one option here is to train a few models which are much smaller in size than your large model, and then see how to transfer the hyperparameters of these smaller models efficiently from small to the large scale. And one method that's used here a lot is this mu transfer method. Another issue I want to touch upon here is also the overfitting problem. So usually you evaluate the performance of a hyperparameter configuration on a dataset that stays fixed. And if you run lots and lots of trials, you can also, of course, overfit to that validation dataset. Some techniques to avoid that include building post hoc ensembles. So taking a certain number of models and averaging their prediction after training. Instead of measuring the performance on a fixed validation set, you can also do cross-validation, but this is of course very, very computationally expensive, as you need to rerun your training or your evaluation for each cross-validation split. And what I've actually also seen in my research is that using lower than single precision calculations, such as half precision, can also improve the generalization performance of your HPO loops due to the inherent regularization effect these low precision methods have. Okay, now for the final part on doing hyperparameter optimization on HPC. We have already seen that methods like ARSHA are very scalable in a parallel computing setting, for example, on HPC systems. But when you are on an HPC system and want to run HPO for some machine learning model, there are actually some choices you need to make. And one of these choices is how to allocate your number of GPUs. So when you're training a machine learning model on a large data set, you usually want to use GPUs to do this. And let's say you have a different number of GPUs available, let's say 32 in total. You can then, and you want to do hyperparameter optimization here, you can then either choose to enforce more parallelism on the trial side or on the side of the distributed deep learning. And yeah, when you allocate more GPUs to the distributed deep learning loop, your models, each single one of your models will run faster, as I think you've already learned in one of the earlier lectures. But then if I have a fixed number of GPUs, using more GPUs per trial means that I have less trials running in parallel. So if I use 8 GPUs for the distributed deep learning loop of my neural networks, and I have 32 GPUs in total, I can just run 4 trials in parallel. On the other hand, I could also enforce more parallelism on the HPO level. So I can take just 4 GPUs for the distributed training of my models, but then have more trials running in parallel. So if I use 4 GPUs per trial, that would mean I could afford to run 8 trials in parallel, but then each of these trials would, of course, train much longer because it's just using 4 GPUs instead of 8 GPUs. And you can alleviate this trade-off a bit by, again, going back to the concept of successive halving. What's usually done in the literature is that successive halving is mostly applied in the time domain. Again, what I've shown earlier, this means that better models are just trained for more epochs. And this is shown in the left plot. So bad performing configurations are terminated and the better ones continue training. It is, however, also possible to add a spatial component to this successive halving loop and perform a successive halving in time, while at the same time performing a successive doubling of the compute resources in space. And this is shown on the plot here on the right, where again we terminate the bad performing trials. But what we now do is to take the GPUs of these terminated trials here and give them to the training loops of the better trials, of the trials that are allowed to continue training. And what this will do is actually accelerate the runtime of your better performing trials, because now they have more GPUs to run in parallel. When you're just doing a successive halving in time, like in the first approach on the left here, the problem is that when doing HPO on large data set, sooner or later you will actually run into idling GPUs, because the trials that are stopped don't continue running, and then at some point in time there will not be any more trials you can allocate to these idling GPUs, and these low GPU usage results in a less efficient usage of your computing resources, and is also not liked very much by HPC administrators. Now, however, if we take the second approach that I introduced and combine this successive halving in time with a successive doubling in space routine, this algorithm is called resource adaptive successive doubling. You actually avoid the idling of GPUs by assigning the free GPUs to the distributed deep learning loop of the trials that continue training here. The nice thing, of course, is that now the trial that was allowed to continue has not only 4 GPUs to train on, but a total number of 8 GPUs after the first successive halving step. So assuming ideal scaling, it will now run twice as fast. And we can, again, not only do this at one point, but actually at multiple points in time. So that after another successive doubling step, this trial will actually run not on 8 GPUs, but on 16 GPUs at the same time. And then compared to the initial training time of running just on 4 GPUs, it will get a speed up with a factor of 4, which is, of course, quite significant here. And yeah, in general, this method is very suitable for application on parallel computing systems, such as high-performance computing systems, where, of course, you have lots of GPUs available that can you can leverage to run your hyperparameter optimization. Okay, now I finally want to wrap up with some practical insights that I want to share with you. I combined these based on my experience of running hyperparameter optimization workloads on HPC systems for quite some time now. The first one is to optimize these classical optimizer-related parameters and the parameters of your architecture at the same time. So to not just do new architecture search or classical HPO, but actually fuse those two things together, because often they heavily influence one another. So you won't get the joint benefits of running both things at the same time if you choose to do this differently. Then for these efficient successive halving or successive doubling algorithms, it's usually worth it to try out different levels of aggressiveness here. So in the examples I showed you, I always continued training the best 50%, but you can usually be even more aggressive and keep only the top 30% or even just the top 25% of the best performing trials and just cut off the rest. One thing that's also important is to not treat the batch size as a hyperparameter. So in general, smaller batches will give you a better generalization performance, but require more compute, as they cannot fill up the GPU memory. And especially on modern GPUs, larger batch sizes are more computationally efficient. So the best thing to do here is to actually increase the batch size to as much as your GPU can handle, and then instead focus on optimizing the learning rate. The next point is to select your search space intervals with a lot of care. And one example here is the weight decay value, which you find in the classical SGD optimizer. This value is extremely sensitive. If you choose an interval that is too large, basically all your hyperparameter configurations will result in a bad performance if this weight decay value is too large. And then you cannot get any information of your HPO run, because even though all your other hyperparameters might be really optimal, if your weight decay value is bad, none of these good hyperparameters will matter, and your training will probably even diverge. And I want to finish with the last but most important point, which should be clear, but I want to mention it again, that when you're doing HPO, you need 3 data sets. You first need a training data set to train your models on. Then you need a validation data set to validate the performance of your different hyperparameter configurations, and then pick the best hyperparameter configuration based on this validation set performance. And finally, you also then again need a completely untouched test data set where you take the best hyperparameter configuration that you found from the validation set and then again test it on the test set. And the test set score is the model score that you want to report for your model. This is the final score your model gets. Training performance and validation performance are not so important because they are of course biased when you do lots of hyperparameter optimization, but this test set performance is the value which is then representative of your model performance. Yes, this was my last slide, and with this I thank you for your attention and see you soon. Bye bye.